How's the signal?
Pretty good, buddy. I hear you loud and clear.
Welcome back to today's material, where we will be talking about the divergence test. Now, by the end of today, we only have two goals. One, we want to use the divergence test to show that a series diverges, and we want to identify logically invalid uses of the divergence test. So this video is probably going to come out a bit shorter than the rest. But I really want to focus today just on this singular test, because I tell you, I think this test might be cursed.
This place is cursed.
What is it with you and curses?
I find that students are more likely to misuse this particular theorem than they are to misuse any other theorem in the entire course. So please pay close attention to the hypothesis and the conclusion of this theorem to make sure that you are using it correctly whenever you do use it, because this theorem is mysteriously somewhat perilous. It's very easy to use this incorrectly. The divergence test, the advantage of this test is that it's very easy to use. The disadvantage of this test is that it's useful in very few situations. So it's easy to use, but not very broadly applicable. I'm going to state this theorem clearly in if-then notation, so that there's absolutely no confusion about what the hypothesis is and what the conclusion is. The theorem has two parts. Part number one. So if you have a sequence, let's call it A sub k. And suppose that this sequence diverges. The sequence doesn't actually converge upon any particular number. If the sequence diverges, then the associated series must also diverge. Regardless of starting position, if the sequence AK diverges, then the series, sum of AK, also diverges. So the hypothesis is that the sequence is divergent. If the sequence converges, then this part of the theorem is still locked. You cannot make any conclusions at all. The divergence test has a second part, though, which says if the sequence AK converges to any number except for 0, then the series diverges in that case as well. Okay, divergence test says when you start working with a series, if you're trying to get some quick information about whether the series is divergent, first look at the sequence. Look at the sequence of terms that you're adding up. If the limit of the sequence does not exist, or if the limit of the sequence is anything other than 0, then you can safely conclude that your series diverges. So let's go ahead and have a look at some applications of the divergence test, and let's see if they're logically valid or not. Okay, are the following uses of the divergence test logically valid or logically invalid? This person is considering the sequence where the formula for the sequence is that a sub n is equal to cosine of n. And they note the fact that as n goes to infinity, this sequence is divergent. The terms in the sequence continue to oscillate forevermore because cosine oscillates forevermore, and therefore this limit does not exist. They conclude that by the divergence test, the associated series, the sum from whatever starting point to infinity of cosine of n, that series must also diverge. What do you think? Is this logically valid or not? This one is logically valid. As soon as they deduced that their sequence of terms did not have a limit, the first part of the divergence test unlocked. And once the divergence test unlocked, it was safe to apply that conclusion, which is that the associated series must also diverge. No problems here. Let's look at the second application. The second application, the student is looking at the sequence of terms whose formula is given by 1 over 1 minus n. That nth term in the sequence is given by this formula. They notice the fact that as n goes to infinity, this sequence of terms begins to approach 1 in value, because the 1 over n is going to 0 as n goes to infinity. They say the sequence converges to 1, therefore the series that I get by summing up the terms in that sequence must also diverge by the divergence test. What do you think? Logically valid or no? Once again, this one actually is logically valid. The student has discovered that this sequence converges to a number that's not 0. So the hypothesis of the second part of divergence test is satisfied, and that part of the test is unlocked. Because the divergence test part 2 was unlocked, it was safe to conclude the conclusion of that part of the test, which says your series must diverge. So no problems here. Now let's have a look at the third application. As n goes to infinity, the sequence a sub n equals 1 over n converges to 0. Therefore, is it safe to conclude that the associated series found by summing up 1 over n is convergent? This application is not logically valid. And actually, as a matter of fact, this conclusion is wrong, which is what we will see in our next video. This series actually does diverge. It goes to positive infinity. So what's wrong with this application? Where did this student make a misstep? This student made a misstep trying to use the divergence test even though it was never unlocked. The sequence that they were considering converges to 0. Because the sequence converges, the first part of the divergence test is still locked. And because the sequence converges to 0 in particular, the second part of the divergence test is still locked. In other words, neither one of these two hypotheses is satisfied. It is not true that the sequence diverges, and it is also not true that the sequence converges to a number that's not equal to 0. Neither hypothesis is satisfied. Because neither divergence test hypothesis is satisfied, this theorem is still locked. It is completely useless to us in this problem, and we need to throw it away and not use it in this problem at all. Div test is locked. We can't use it even slightly. Let's look at the fourth application. The student in this case is investigating the sequence a sub n equals 1 over 4 to the n. as n goes to infinity, and we take this fraction to progressively larger powers, this sequence converges to 0. Must it therefore be true, from the divergence test, that the series that we get by summing up 1 over 4 to the n, is it true that that series must converge by the divergence test? This is not a logically valid application of the divergence test. Once again, the sequence converges to 0, which means that neither of the hypotheses of the divergence test are satisfied. Which means that referring to the divergence test in this problem is completely inappropriate. So their argument is incorrect. Now, their answer is actually right. This series actually does converge. But the student's rationale, their argument, their reasoning is flawed. The real reason that this series converges, the valid argument that you could use to convince the skeptic, is that this series is geometric. With a common ratio that is less than 1 in magnitude. So the reason that this series converges is not the divergence test. This series converges because of the theorem from yesterday, which says that geometric series converge whenever their common ratio is less than 1 in magnitude. Now, if you're on an exam, if you're on a homework assignment that I am grading, and you give me work like this is going to receive very little credit. Because guess what? I am the skeptic. I am the one who's going to be looking at your work and trying to find logical holes in it. So something like this would probably only receive 25 to 50%. No, I think an error this bad would only receive 25% of full credit. Because I am grading not just your conclusion, but I am grading your entire argument. Are all the steps in your argument logically valid? That's what I'm looking for on the exam. So if you give me something like this where the answer is correct, but the argument is incorrect, that's not going to be worth full marks. It's probably only going to be worth about 1/4 of full marks. Okay, exercise. Let's look at a couple of series and let's see what we can logically, validly conclude. What we can conclude safely about the convergence/divergence of the series using the divergence test. And here we have the series that we have obtained by adding together various terms of the sequence 1 over n squared. Now, just as an aside, within these kinds of problems, where we're not trying to find the value of the series, we're just trying to decide whether or not it converges, you'll probably see me omit the limits on the top and the bottom of the sigma. That's because the convergence of a series is not affected by the series starting position. The starting position in the series affects the value of the series, but it does not affect whether or not the series has a value. So in questions like this, where I'm just asking about convergence/divergence, you'll probably see me omit, for simplicity's sake, the starting value, because it really doesn't matter. Okay, so here I have the series where the associated sequence is 1 over n squared. Now, as n goes to infinity, this sequence converges to 0 because I'm just dividing by increasingly large numbers. Now, because this sequence converges to 0, neither of the hypotheses of the divergence test are satisfied. So this test is still locked and inaccessible, which means what can I conclude about this series using the divergence test? I can conclude absolutely nothing about this series because the divergence test is still locked. Okay, let's do the next example where we have the series of the sequence n plus 3 in the numerator, n plus 2 in the denominator. So in this case, if we consider the limit of the sequence that we're summing up, we can apply L'Hopital's rule, take the derivative of the numerator, take the derivative of the denominator, and we get the number 1. The terms in this sequence approach the number 1, which is not 0. So the divergence test is unlocked. The second part is unlocked because our sequence converged to a number that was non-zero. Therefore, it's safe to conclude by the divergence test that the associated series must diverge. Okay. Now let's have a look at the third series where the sequence is given by e to the n at the top and n at the bottom. Now, as n goes to infinity, once again, we can use L'Hopital's rule to take the derivative of the numerator and the derivative of the denominator. But because e to the n is growing without any limit, this entire quantity is growing without limit. So, this sequence of terms diverges to infinity in this case, which means the divergence test is unlocked. And by the divergence test part 1, we know that the series must diverge. And similarly, we have the sum of 2 to the n the terms in the sequence go to positive infinity, so the divergence test is unlocked. And once again, we can safely conclude that this series diverges. On something like an exam or on a cumulative weekly homework, you're going to be given a series and you're going to have to figure out which of our many different techniques and tests you can use to make a logically valid conclusion about whether the series converges or diverges. So let's get some practice with that, and let's try and figure out which technique would be the most appropriate to decide and prove whether the series converges or diverges. Let's write a formal argument. Let's convince the skeptic. In other words, convince me. Our first series is the sum of the sequence 3 over 4 to the n. Now, if I try and apply the divergence test, if I have a quick look at the limit of the sequence is 0, which means that divergence test is still locked, and within the context of this problem, it is completely useless. So if I want to decide whether this particular series converges or diverges, I have to use some other technique, some other theorem, some other test. Notice that this series is geometric. With a common ratio of 3/4, which is less than 1. So as a result of that, we can conclude by that theorem on convergence for geometric series we can conclude from that theorem that the series must converge. Okay, let's try it with the second example, where the associated sequence is 1 over n squared plus n. Now if I quickly look at the limit of the sequence, then the limit of the sequence is going to 0, which means div test is useless, still locked up. Likewise, this series is not geometric. It's not in the form of number to a power, which means that the theorem for convergence of geometric series is still locked. So what other kind of series have we encountered in our work so far? The other kind of series that we have encountered so far is a variety called telescoping. So let's have a look at this series and let's check and see if it might be telescoping. The first thing that I'm going to do is I'm going to factor this denominator and pull it apart using partial fractions. So I'll have n plus 1 and n for the two denominators, and I think if I have negative 1 here and positive 1 here, then these two expressions will in fact be equal. So if I wrote out a partial sum up to the number capital N, then I would have some starting number and then after that I would have the next terms, and so on and so forth, all the way up to the final term, capital N, where I would have negative 1 capital N plus 2 plus 1 over capital N plus 1. Which means that the partial sums are always going to simplify, so that the only thing that survives is the very first term, positive part, and the very last term's negative part. But the last term's negative part, negative 1 over capital N plus 1, goes to 0 as n goes to infinity. So the partial sums approach whatever this initial number is, 1 over whatever, as n goes to infinity, and the series converges by definition. The meaning of a series converges, the meaning of that term was that the limit of the partial sums existed. So by analyzing the partial sums of this telescoping series and concluding that the partial sums approach a finite number, then the definition tells us that the series converges. Okay, series number 3. What can we safely conclude? If we look at the limit as n goes to infinity of the associated sequence, then once again using L'Hopital's rule, we can take the derivatives and we get 2 over 1. So the sequence here, the sequence of terms that we're adding up, approaches 2, which is non-zero. Which means, haha, the divergence test actually is unlocked. And we can safely conclude that this series must diverge. Now, let's reflect on what we have done just for a little bit. Let's go back and let's make a notation next to all the logically valid applications of the divergence test. We have just done a logically valid application of the divergence test, and we concluded that the series diverges. In this problem with 2 to the n, when the divergence test was unlocked, we concluded that the series diverges. In this problem, when the test unlocked, we concluded that the series diverges. In this problem, when the divergence test unlocked, the series diverges. In this example, the divergence test was unlocked and we concluded that the series diverges. In this second problem, when the divergence test was unlocked, we concluded that the series diverges. One of the big takeaways from today, one of the things that I really want you to sow into your heart, is that if you ever conclude that a series converges by the divergence test, that's definitely logically invalid. It is always invalid to use the divergence test to make the conclusion that a series converges. So the divergence test can only be used to show that a series must diverge. If you want to show that a series converges, you need a different test. Divergence test cannot help you. The second major takeaway is that so far we really have 3 main techniques to analyze a series and determine whether it converges or diverges. First of all, the definition, to write out a formula for the partial sums and take the limit. We have this theorem on divergence for geometric series, and we have the divergence test. But there are still a lot of series that cannot be analyzed using just these 3 techniques. For example, all the series here, the sum of 1 over n, the sum of minus 1 to the n over n, the sum of 1 over n factorial, and the sum of n to the n over n factorial, none of these can be analyzed using the techniques that we have so far. Which means that we need more techniques that can be used to decide whether or not each of these series is convergent or divergent. So by the end of the chapter, we're going to have, I think, a total of 9 different techniques. And your job, I think probably the hardest part of midterm 1, will be to figure out which technique you will need to apply to any particular series that you are given on an exam. So I encourage you, as we go through this chapter, to begin to do some note-taking and to do some thinking about when a technique is useful. What kind of series would you have to have in order to apply each technique? In sum, what have we done today? We have introduced the divergence test, and we have talked about logically valid and invalid uses of this test. We have also practiced applying divergence test correctly, and we have practiced, given a series, deciding which of the 3 techniques we have so far can be safely applied to the sequence that we've been given.